The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Ladies and gentlemen, welcome to lecture number 11. In this lecture, I would like to continue discussing with you the solution of the dynamic equilibrium equations. We discussed the solution of dynamic equilibrium equations already in lecture number 10. In that lecture, we considered direct integration methods. In this lecture, I would like to discuss with you the mode superposition analysis. The basic idea in the mode superposition analysis is the transformation of the U, or from the U displacements into a set of new displacements x. P is an n by n matrix which is non-singular. If P is non-singular, we should recognize that the vector u of length n is uniquely given when we have the vector x also of length n, and vice versa. In other words, if we have the vector x, we can calculate u, or if we have u, we can calculate x. P, of course, has to be a non-singular matrix. We call this a transformation matrix. And we call the x displacements that I will be talking about the generalized displacements. Now, if we use this transformation, we find that if we substitute this transformation into this equation for u, and we postulate that P shall not be a function of time, so that when we find the derivative of u with respect to time, let me denote it by a dot here, we simply obtain that u dot is equal to P times x dot, and similarly u double dot is equal to P times x double dot. If we then substitute for u, u dot and u double dot, in other words for the displacements, velocities and accelerations, into this equation, we obtain this equation, provided, and now there is one additional step, after the substitution for the displacements, velocities and accelerations, we also pre-multiply the total equation by a P transposed. In other words, what we do is we take a P transposed here, and we are substituting for these vectors here from that relation here. The P transposed, of course, gives us also a P transposed R on the right-hand side. So R curl here is defined as shown down here. Notice that the M curl, C curl, and K curl are given as shown here. And they involve, of course, the M, C, and K matrices. And this P here comes via this substitution into these vectors. This P transpose comes from that P transposed here. Now, what have we been doing so far? Basically, what we have been doing is we have changed bases. We have gone from the displacement defined by the finite elements, by the finite element nodal points, to generalized displacements. The generalized displacements now govern the equilibrium of the system. Now, this transformation is effective if we find that our M curl, C curl, and K curl have a better structure than the matrices M, C, and K. And of course, if it is simple to find the P matrix, or a P matrix. If, for example, let's look at the very simple case. If, for example, M curl, C curl, and K curl would all be diagonal matrices, then the solution of this set of equations would be very simple. In fact, this is our objective. It is our objective to come up with a P matrix which, when used in this transformation, gives us an M curl, C curl, and K curl matrix that are all diagonal. And of course, in addition, we want to find the P matrix with the minimum amount of effort. Once we have diagonal matrices here on the left-hand side, in other words, M curl, C curl, and K curl, then we can use our direct time integration schemes, the Newmark method, or the central difference method. Usually we use the Newmark method. Or we might even be able to solve the decoupled equations. They're decoupled because M curl C K curl are diagonal. We might even solve these equations in closed form. The question then is, how do we find P, or a P? We want to find it cheaply. It shall be economical to calculate P. And we want to, of course, have that M curl, C curl, and K curl are ideally diagonal matrices. Well, the P matrix can be constructed, or a P matrix can be constructed effectively by looking at the free vibration equilibrium equations of the system. If we look at these equilibrium equations here, in which we neglect damping and we neglect the right-hand side forces, we're looking at the equilibrium equations of the dynamic system without damping and without forces applied. And if we look for a solution to this system, then we can assume a solution of this form, u of course being our displacement vector, phi being also a vector that is independent now of time. And here is the time dependency. Sine omega, omega is a radian per second, a circular frequency, t of course being the time, and t0 is a time shift. If we make this assumption, substitute into here, but when we do substitute, of course, remember we have to take the second derivative of this function here with respect to time, because we're taking the second derivative of u here. And that gives us a minus omega squared sine omega t minus t0. Substituting from here into there, we immediately get this equation, because we can cancel out sine omega t minus t0 on both sides. This is the resulting equation. So what we now want is to solve for phi and omega squared. This is the generalized eigenvalue problem. The generalized eigenvalue problem because M is a matrix other than the identity matrix in general. And we know that there are n solutions to this problem if K and M are n by n matrices. There are n solutions to this problem. We call these solutions the eigensolutions. And we call omega 1, phi 1, or omega 1 squared, I should say, and phi 1 the first eigenpair. This is the second eigenpair. This is the nth eigenpair. There are n such eigenpairs. Each of these eigenpairs satisfies this equation here. Therefore, these are a solution. We call it an eigensolution to this equation. And in addition, we also can prove, we can show that the phi I vectors, these vectors here, are M orthogonal. M orthogonal because phi I transpose M phi j, for example, phi 1 transpose M phi 2 is equal to 0. And phi 1 transpose M phi j, phi 1 transpose M phi 1 is equal to 1. And because it's equal to 1, they are not only M orthogonal, they are indeed even M orthonormal. What we find is that if we look at this eigenproblem and we notice that a certain vector satisfies this eigenproblem, then also a multiple of that vector satisfies the eigenproblem. And we determine this constant, this undetermined constant, in such a way as to have phi I transpose M phi I equal to 1. So these are the eigenpairs, and the eigenvectors, phi 1 to phi n, satisfy this relation. The eigenvalues, omega 1 squared to omega n squared, can be ordered in this way, where we find that we might have multiple eigenvalues. Omega 1 might be equal to omega 2. But if we do, we still have only a total number of n such eigenvalues. I will discuss in the next lecture with you the solution techniques that we're using to calculate these eigenpairs. Let's for the moment assume that we have calculated them and we want to use them. Well, if we now define the following matrix, phi, capital Phi, it's a capital Phi because we're seeing crossbars top and bottom here. If we define this matrix as phi1 to phi n, in other words, we're taking the first eigenvector and list it as the first column of this matrix here. The second eigenvector we list as the second column in this matrix, and so on, so that we find, of course, that this matrix here is an n by n matrix. And if we define a diagonal matrix omega squared, this is a capital omega squared being equal to zeros in the off-diagonal elements, but the diagonal elements being omega 1 squared to omega n squared, then we can write the solutions to the eigenproblem. The solutions to the eigenproblem, and I'm still talking about this eigenproblem here. We can write the solutions to these eigenproblems, to this eigenproblem in the following form. Notice that this omega squared here has to be on the back of the capital Phi. In other words, this is here the solution to the problem k phi equals omega squared m phi, where the omega squared is a scalar and appears here in front. We usually write it in front. Of course, we can put it also at the back because it's a scalar. We can put it in front or the back. However, when we have listed the solutions to this problem in this way, then we have to put the capital omega squared at the back of m times phi. You can verify that by simply multiplying out the right-hand side. We also have this relationship here, which is the m orthonormality, the phi orthonormality with m. In other words, this here says nothing else than phi I transpose m phi j is equal to delta ij. We call this the Kronecker delta, and this Kronecker delta is equal to 1 for I being equal to j, and it's 0 otherwise. So we are having this relationship here. And if we use this relationship and we are pre-multiplying this equation by phi transpose, the capital Phi transpose now, both sides, we are finding that we are getting here the identity matrix, and therefore we are having that this left-hand side is equal to omega squared, this matrix here. And this is an important fact. In other words, we find that the vectors, the eigenvectors, satisfy these two relationships. Now, if we look back at what we started off with in our mode superposition analysis discussion, we wanted a matrix that we called P, which is such that P transposed M, P ideally is a diagonal matrix. Well, we have now such a matrix. If we take phi being equal to P, then phi transposed m phi is in fact a diagonal matrix. In fact, a very nice diagonal matrix, the identity matrix, which is a matrix that is diagonal and has just once on the diagonal. Similarly, we wanted here that P transpose Kp is a diagonal matrix. Well, we have achieved that by this phi matrix. So the phi matrix is indeed a particular P matrix that we can use. So what we are then saying is, let us use in mode superposition analysis this particular P matrix. The P matrix which is equal to the phi matrix, and phi storing the eigenvectors of the generalized eigenproblem. Well, then substituting from here, as before, into the governing dynamic equilibrium equations, we directly obtain this equation, where, however, we notice now that this matrix here, in general, is not yet a diagonal matrix. We call that our C curl, and our C curl has not been diagonalized yet. We will have to deal with that matrix still a little later. How do we solve these equations? Well, if we solve these equations, we have to also recognize, of course, that we have to include the initial conditions to the problem. And the initial conditions mean that the initial displacements are defined and the initial velocities are defined. These, of course, are the initial conditions that are used in the direct integration solution of the governing dynamic equilibrium equations. Well, if we are now performing the solution of this set of equations, we will have to transform these initial conditions to initial conditions on the generalized displacements. And that is achieved via these relations here. Let us see how do we derive these. Well, if we look at this equation here, and if we notice that, of course, this equation must be applicable for time 0, we can simply put a 0 there, and we put a 0 there. Then, of course, we also recognize that we can pre-multiply this equation with this relation here. And if we do that on the right-hand side, we notice that phi transpose m times that phi is the identity matrix. And so we have this relation directly obtained. The left-hand side in this equation is the right-hand side in this equation, and the right-hand side here is simply this 0x now. The same holds also for the initial velocities. We can simply put dots on top of the u here and of the x, and therefore we have this relation here. So the solution of this set of equations, and with these initial conditions subject to these initial conditions, gives us the solution of the dynamic response. Now, I should mention here that we still have to deal with the damping matrix. The damping matrix here needs particular attention. We do not have in general a diagonal matrix here, and we will want to construct specific damping matrices with which we can deal effectively, and yet, of course, these matrices must make physically sense. Let us look now, however, first at the case where we neglect damping. When we neglect damping, we have this set of equations, n individual equations of this form. Notice that these are n individual equations because this is a vector, this is a diagonal matrix, and on the right-hand side, we simply have a vector of loads, of course time dependent. So we can look at the first row in this matrix relation, and the first row in that matrix relation will be this equation here with I equal to 1. The ith row in this relation here is the ith equation here, in other words, I subscripts on these variables, and in general, therefore, we want to solve n such equations, I going from 1 to n, with this being the load vector, and of course with these initial conditions. These initial conditions are obtained by simply looking at this equation here and extracting the ith row from each of these two relations. So this is then the problem. Notice the following, that if we solve all n equations with these initial conditions, then if we use, for example, the Newmark direct integration method on these equations, we would obtain exactly the same solution as if we had solved the fully coupled equations. The fully coupled equation, let me write them down once more here, plus Ku equals R. In other words, whether we apply the Newmark time integration scheme, a direct integration scheme, to this set of equations with the initial conditions on u and u dot, or apply the Newmark direct time integration scheme to this set of equations, or rather this one here, with these initial conditions, we obtain exactly the same response provided we use the same time step, delta t, in both integrations. There has been no assumption so far. All we have done is a transformation from the u displacements to the x displacements. And this transformation is effective if we can find the phi matrix that we're using in the transformation very cheaply, very economically. Well, the effectiveness really of mode superposition goes beyond what I have just described. The important point in mode superposition analysis is that we do not need to solve all of these equations, that we do not need to solve and look at all of the decoupled equations. But let us look first once also at how we can solve the decoupled equations now exactly. Well, we can solve them exactly, for example, using a Duhamel integral formulation, as shown here, xi of t is given via this relation here. And we would, of course, substitute our Ri of tau, where we now assume that this part here is given directly. In a computer program, very frequently, Ri would only be given as a segment of straight lines. And if that is the case, then, of course, we might have to still evaluate all of this here numerically if the segment is very complicated, complex, like in an earthquake analysis, Ri might be varying very rapidly, and then we might still want to evaluate this numerically. However, in general, we can evaluate here this relationship analytically, and we don't need to use numerical integration. Having got xi, of course, we get our u of t as shown here via transforming back. Well, the important point that I now like to get back to you and discuss with you for a little while is that we do not need to use or to solve all of these equations in mode superposition analysis. In fact, mode superposition analysis is only effective when we do not need to look at all of these decoupled equations. If we have to solve all decoupled equations, then we would have to calculate, of course, first all eigenvalues and eigenvectors, which can be an enormous expense, and then the mode superposition analysis would not be effective. I like to repeat, however, if we do solve all equations, all decoupled equations, using a specific time integration scheme with a specific delta t time step, then if we use the same time integration scheme on the coupled equations with the same time step, we must get exactly the same response. Then there has been no assumption so far. Well, however, if we then do neglect some of the equations here, we do not solve some of the equations, then of course our response will be different that we are predicting via this approach when we compare it with the response predicted via solving these equations. Well, let us look once at this graph again, which we already looked at briefly in the last lecture. And I would like to explain to you now why it is not necessary to solve all of the decoupled equations in mode superposition analysis, why it is not in general not necessary. Well, if we look at a single oscillator equation as given here, I included damping here, of course psi can be equal to 0, where p is the driving frequency, omega is the frequency of the oscillator itself. And if we plot the maximum dynamic response observed, the maximum dynamic response, which we define as the dynamic load factor when we divide that maximum dynamic response by the static response, we get this set of curves. Let us look at, say, the curves psi equal to 0 a little bit closer. If we do that, and if we solve this equation with psi equals 0, this term now not being there, for certain values of p over omega, we are getting this curve here and that curve here. What do we notice? Well, we notice that when p over omega is equal to 0, we are getting the static response. Or p over omega very small, we are getting the static response. This means, of course, that omega, the system frequency, is much larger than the applied frequency, which means really that this oscillator is extremely stiff. It's extremely stiff. Well, and when compared to the frequency of load application. So then we are in this range, and we notice that, say, p over omega in this range here, smaller than a certain value, this is here 0.5, say smaller than 0.2, we would see that basically the maximum dynamic response is really just nothing else than the static response. So we are talking in this region here really about a static response, and in this region here we are talking about a truly dynamic response. Now what does that mean? Well, if we look at our decoupled equations here, it means that if Ri has a frequency, consists of frequencies basically, which when measured on the system or the oscillator frequency are very small, we basically would have a static solution. We would basically have a static solution for this equilibrium equation. A truly dynamic solution will only be obtained when P, in other words the frequency of the load, divided by omega, falls into this range here. Well, and this is what we are using in mode superposition analysis. We only need to consider those frequencies of the system, and these are the frequencies of the system, the omega i's, which are truly excited by the dynamic loads. We only need to look at those decoupled equilibrium equations for which we have that the frequencies in the decoupled equations are truly excited by the dynamic loads. Now, I only talked about the p value here. Of course, in an actual analysis, we would find that Ri of t contains a number of frequencies, a spectrum of frequencies. Well, what we have to do is we look at the highest frequency that is contained in Ri, and we measure that highest frequency on the frequencies of the system. If that highest frequency divided by the frequency of the system is falling into this range here, we are talking about a static response basically, and we do not need to consider that part, that equilibrium equation, or those equilibrium equations in our mode superposition analysis. Well, so what we are then saying is, let us solve these equations not from I equals 1 to n, but from I equals 1 to p. And then, instead of obtaining the, so to say, true response, the exact response, exact in quotes of course, we are obtaining a response up. I equals 1 to p, phi I xi gives us up, where up is an approximation now to the u displacements. Is an approximation to the u displacements, and the u displacements, once again, are the solution to this system of equations. To this system of equations. How can we find out the error? Well, if up is a solution, or an approximate solution to the system of equations that we want to solve, then let us substitute back into that system of equations. Let me write it down once more here. We have mu double dot plus ku equals r that we want to solve. Well, we can also write that, of course, mu double dot plus ku minus r, and this shall be 0. So if we have an approximate solution to this set of equations, why not just substitute that approximate solution in here and see how large the right-hand side is? If it's exactly 0, well, then we have that our up is indeed very close to u, and if it's exactly 0, of course, up would be equal to u. We will not find this to be 0. We will never find it to be 0 because in a computer we would, of course, use finite digit arithmetic to evaluate the left-hand side, and we would have at least round off. But what we want is that the right-hand side calculated, which we now might call some value, shall be 0, shall be close to 0. And that means really what we want to measure is this part here. Now, what have I written down here? I have here epsilon p of t being this vector here. This is a vector, and we can call this an out-of-balance load vector divided by the applied load vector. Notice that what I'm doing here, I take a norm of that, a norm of this vector, because I want to get a single number. I want to get a single number here, which is representative of all the elements in that vector. The same applies here. The norm is calculated, this norm is calculated by taking each value in this vector, squaring that value, adding the squares of the values up, and then taking a square root out of that final value. In other words, if we write it down here quickly, what we do is, if we have a vector A and we want to find this norm, what we do is we take a1 squared plus a2 squared, etc., add all the individual entries up of that vector here, the squares of the entries up, and then take the square root out of it. And that gives us a single number which is representative of all the elements in that vector. notice that if one element is large, well, then this value must be large too, because that one element will make this value large here. Well, if epsilon t is close to 0, assuming that r of t is not 0, of course, otherwise you couldn't use this, you would have to use some equivalent approach. If epsilon p is close to 0, then we know that our equilibrium equation has been solved quite accurately. In general, we might find that it is not close to 0, and what we want to do is a static correction. This static correction takes into account the fact that we have neglected the higher modes, and in the higher modes, of course, we know we have basically static response. That's why we did not include those equations in the mode superposition analysis. So what do we do in that static correction? We recognize that r could be written in this form. This Ri is exactly the value that I defined earlier. M phi I is a vector. You see, I can take m and multiply it by phi I, and I get a vector. Now, there are n such vectors. We might not have calculated all n, but we can say that indeed, in theory, there are n. Well, so we can write this down. We also then can calculate the delta r, which is that amount of the load vector which has not been included in the mode superposition analysis. How do we obtain it? Well, we know r is the total load vector, and if we now sum, instead of I equals 1 to n, only from I equals 1 to p, we are getting this part here. But this part is exactly what we have included in the mode superposition analysis already. So we are left with a vector on the left-hand side, which we have not included in the mode superposition analysis. And we did not include it because we knew at most we can have static response corresponding to these loads. Let us now calculate that static response. And that's done right down here. Now, this static response has to be added to the response which we predicted in the mode superposition analysis. Let us now go to the case with damping included. So far, we neglected damping. Now, with damping included, we have this part here too. Notice phi transpose C phi in general is not a diagonal matrix, and that's why I considered first the case without damping. However, if we have proportional damping, and in structural analysis, frequently all that is necessary is to include proportional damping, which we postulate to be of this form, 2 omega I psi I. Delta ij is again the Kronecker delta, which is equal to 1 when I is equal to j and is equal to 0 otherwise. So if we are postulating this, where omega I, of course, is given, that is the free vibration frequency, which is stored in this matrix here. Psi I is a value, which we are not given yet. We have not discussed it yet. But if we postulate that this matrix here, basically, or each entry in that matrix can be written in this way, then indeed we would have decoupled equations. It turns out that in practice, as I mentioned just now already, this is all that is necessary to include damping appropriately. Well, if we know these psi I values, then we can also construct a C matrix. We can also construct a C matrix with the psi I values given. The psi I values are frequently obtained from experiments. In other words, a structure is taken, it's vibrated, it's excited into certain vibration modes, and from these experiments then we obtain the psi I value. So once we have the psi I value given, we can calculate a C matrix. And one way of calculating it is to use the Kogi series. Here we have the Kogi series, which was proposed for calculating a C matrix which satisfies this criterion. In other words, damping is proportional. Well, if the psi I values are given, we can calculate the omega I, of course, are also given. We can calculate, using this equation, the constants A0 to AP minus 1. Once we have these constants, we can substitute them into here, and we're coming up with a C matrix, and this C matrix here indeed satisfies the orthonormality property shown here. So, in other words, given the xi I values from experimental results, given the omega I values, we can calculate a C matrix that in fact gives us a diagonal matrix when we carry out phi I transpose C phi j. A special case of this C matrix is Rayleigh damping, used abundantly in practice, where we just include the first two terms, alpha and beta being constants now. Let us go through a particular example. Let's say that we know that the critical damping psi1 is 0.02 and psi2 is 0.10. In other words, 10% critical damping in the second mode and 2% critical damping in the first mode. The corresponding frequencies are 1 and 3. We want to calculate alpha and beta. Well, what we do is we use this C matrix in the relation phi I transposed C times phi I. And that shall give us 2 omega I psi I. Of course, we have two I values, I equals 1 and I equals 2. So we can apply this equation twice. Well, when we calculate it out, we get this. Applying it twice, we directly obtain these two equations here. And we solve these two equations for alpha and beta. Having got alpha and beta, we can substitute now back into this equation here and have our C matrix. This would be, for example, a C matrix that we could use in a direct integration analysis. You see, if we are performing a mode superposition analysis, we might know from experience, from experimental results, that psi1 and psi2 are of these two values. And then, if we know that we have so much critical damping, or so much damping in the first and second vibration mode, and we want to perform a step-by-step direct integration analysis, we would have to construct a C matrix. And this is a procedure to construct a C matrix. Then, of course, we would have to ask ourselves, well, knowing these psi values for omega 1 and omega 2, what are now the psi values that we are implicitly using for the higher modes when we employ this specific C matrix? And we use now this equation here. This is the equation which we already derived on this view graph here by looking at this relation. See, you're now using this equation because this equation must be applicable not just for psi1 and psi2, but for all psi values. Well, then using this equation, we can solve for the psi values, and of course psi1 and psi2, substituting alpha and beta in here, and omega 1 and omega 2 would indeed be just 2% and 10%, 0.02 and 0.10. However, we can now use this equation to get the higher psi values. And there is something to be observed which is quite important. Namely, we notice that the beta value that we calculated is associated with the high frequencies, basically, and alpha here, the alpha value goes away, or this contribution goes away when we are looking at the high frequencies. For high frequencies, therefore, the beta value is the dominant factor, and for low frequencies, the alpha value is the dominant factor. In other words, once again, looking at this equation here, for the in the high frequency response, the k, beta k really will determine the damping, and in the low frequency, it's really response is really the alpha value that determines the damping. Well, the response solution now would be performed in exactly the same way as before, as in the case of no damping. We solve now again P equations only, and we are doing that by looking at this equation, and with, of course, Ri being given as shown here, and the initial conditions being given here. Solving this equation here via numerical integration or exact integration using, for example, Duhamel integral, we obtain the xi values as a function of time. We substitute into here to get our up, which is an approximation to the solution of the dynamic equilibrium equations. the dynamic equilibrium equations now being mu double dot plus cu dot plus ku being equal to r. Notice we have a C matrix in here now. However, and this is an important point, we have a specific C matrix constructed such that the phi I transposed C phi j gives us a diagonal matrix with the diagonal elements being equal to 2 omega I psi I. And one of these matrices, for example, would be the Rayleigh matrix that I just, or the matrix obtained using Rayleigh damping, rather. The important point is, once again, that all we have been doing so far is to make a change of basis, from the finite element coordinates to the generalized displacements xi. That was the first step. The second step was that we are neglecting the modes p plus 1 to n by only solving the first p equations here and using this as an approximation to the actual solution. The important point, of course, is now that we have to ask ourselves, when is mode superposition analysis really effective? And this some considerations I have here summarized on the last view graph. The mode superposition analysis is effective when the response lies in only a few modes. What does this mean? It means that if we look at our eigenvalue problem, k phi equals omega squared m phi, we only need to solve this eigenvalue problem for a very few modes. In other words, p being much smaller than n, I will only have to solve for phi 1 up to phi p and omega 1 squared up to omega p squared. This is a very important point. I assumed here that we are taking the lowest frequencies, omega 1 to omega p. Of course, in general analysis, it might be just necessary to calculate certain frequencies, say omega 10 to omega 20. We only want to find the frequencies in a certain range because we know that the excitation frequency only lies in a particular range. That would be, for example, the case in vibration excitation analysis. This then is a requirement for mode superposition analysis really to be effective. When the response is obtained over many time intervals, then mode superposition analysis also becomes effective. We should remember here that if we perform a direct integration analysis, and if that is an implicit direct integration analysis using the Newmark method, for example, then the number of operations that we talked about, number of operations in the Newmark method, was 1/2 n m squared. That is the initial triangular factorization that we have to perform, m being the half bandwidth, plus 2nm. N is the order, of course, of the system. M is the half bandwidth once again, times t, times the number of time steps. This is an initial expense that we have to perform using the direct integration Newmark method, for example. The same holds for the Wilson theater method or the Hubold method. This is an initial expense. And then we perform this number of operations for each time step. Now, if we have to run 5,000 time steps, then direct integration would be extremely, extremely expensive. And in fact, you might not be able to afford it using direct integration, implicit direct integration. Well, therefore, you can see directly by looking at this operation count, what should make the analysis more effective is to bring down the bandwidth. And of course, this is exactly what we are doing in mode superposition analysis. We are going from a bandwidth of m to a bandwidth of 0. We are having a diagonal matrix. Remember, the bandwidth we defined to be the number of off-diagonal elements here that we are having. We did not include the diagonal. So that is the half bandwidth. If we look at the total band here, that total band here was equal to 2m plus 1. 2m plus 1. So if we are reducing the bandwidths, as we do in mode superposition analysis, then we can see immediately that this number of operations here, which is directly proportional to the number of time steps, goes down. And that is exactly the objective in mode superposition analysis that I talked about earlier. That is the first important objective. We want to reduce the bandwidths for the direct integration analysis. The second objective, of course, is that we do not need to even consider all of the equations. So looking at n, we are reducing n also. We are not looking anymore at n equations. We are looking at p equations, and we are reducing the bandwidths, as I said earlier. M goes to 0, and n goes to p. Of course, this is an approximate count here. So basically, you can see that in the solution using mode superposition analysis, the number of operations in the time integration of the decoupled equations is relatively small, is little, and in fact, this solution here can be obtained very, very effectively. The time integration of the decoupled equations is very effective in an actual practical analysis. Where the expense lies in mode superposition is really in the calculation of the required frequencies and mode shapes. And of course, this is exactly the subject of the next lecture, where I want to discuss with you the effective solution techniques for calculating these vectors and frequencies. Mode superposition analysis is effective altogether only when we can calculate these eigenvalues and eigenvectors in an effective way. I should also finally once again emphasize that it may be important to calculate the error, epsilon pt, that I referred to, or to add a static correction to the predicted response in the mode superposition analysis when p is, of course, much smaller than n. We have neglected the high-frequency response here. That high-frequency response is a static response in general and should be taken into account via, say, static correction, as I have been discussing it with you. This is all I wanted to say in this lecture. Thank you very much for your attention.